Hi folks, welcome to our first longer form video on coding AI ML. Today we're going to run through some easy step-by-step instructions on how to run our lottery ML project. In this project we explore whether or not the lottery can be beaten by machine learning or AI. The spoiler alert, as I revealed in our short form video, is that it can't be, but that does not mean that it's an uninteresting or unimportant thing to pursue. It's a great learning tool. So first thing that you need to do is go to our HonestML coding GitHub, and you're going to want to copy the Git link from the drop-down code bar. I mentioned this in the short, but you don't want to go to the URL bar. You want to specifically copy this one. So what we're going to do is run our command git clone and paste the link. Hit enter. That will download and copy the project as explained in our what is a git clone command short. Then we're going to want to change our directory to lottery ML, matching exact capitalization and spelling of the project. Now, the next thing that we're in the appropriate directory, we're going to want to install the dependencies for this project. In this case, they are torch and numpy. One quick and easy command here, copy this from the GitHub and paste it into your terminal. Hit enter. That will automatically download. A quick warning, Torch is a very large library, so this will take you some time. In this case, I have them pre-downloaded in this rented instance so that I don't have to make you suffer through the pain of watching me download for 10 minutes. So now that we've got everything in the project that we need, we're going to want to scroll down and select the appropriate command for our machine. In this case, I'm running a rented instance with 2 GPUs. With that said, just because I am running an instance with 2 GPUs does not mean that a CPU or 1 GPU model is going to be less valuable to you. So please feel free, try it out with the equipment that you have. If you want to run it with 2 GPUs as I'm doing here, you can rent an instance. I personally use Vast AI. I've found their product pretty good, easily connectable, and they always have machines available to rent. Now, with that said, I have no formal connection with them. I'm not sponsored, but I have been using it for a number of years at this point. So I am quite comfortable with their content. Now, we're going to want to go ahead and copy the first command. So we're silencing the Python warnings in this case. There are a couple of deprecations that have happened in Torch and NumPy over the years. They have no impact on the accuracy or capability of the code in this case. So if that wasn't there, you would see the warnings. However, they serve no purpose in this case, so we're just going to go ahead and silence them. Now, with all of that said, there are a couple of pieces that I want to talk about here before we run this command. The first is the number of layers. The second are the epochs. What do these mean? What do they focus on? So when we talk about layers in a neural network, what we're really talking about is how many stages of transformation the data goes through before producing an output. In this project specifically, each layer takes the input numbers, the lottery results, applies a weighted transformation, introduces non-linearity, and passes a new representation forward. Crucially, adding more layers does not magically create insight. What additional layers do is increase the expressive capacity of the model. They allow it to represent more complex combinations of inputs and interactions than a singular linear transformation, essentially. However, lottery data does not contain deep hierarchical structure in the way that, say, images, language, or audio files do. So in this project, deeper networks are not really learning hidden patterns in the lottery because they don't exist. They are learning how to fit historical noise more flexibly. That means adding layers increases the expressive power and overfitting risk without increasing the true predictive signal. We keep the network shallow not because we're being conservative, but because there's no evidence the data supports depth. An epoch means one full pass through the training data. If we train for one epoch, the model sees each historical draw only once. If we train it 50 epochs deep, it sees the same data 50 times. If we train it for 500 epochs, it sees the same randomness 500 times over. What epochs really control is how hard the model tries to memorize the past data. In data sets with real structure, more epochs help the model converge on meaningful patterns. In lottery data, more epochs mostly helps the model memorize historical coincidences. That means training loss can continue to improve while validation performance does not. And generalization does not exist in the way that people expect. In this project, increasing epochs doesn't make the model smarter, it makes it more confident about the noise that it's seeing. We can cap epochs deliberately to observe convergence behavior, demonstrate overfitting clearly, and show that performance does not meaningfully improve with more training data. Layers and epochs control how expressive and persistent a model is, but they cannot create information that does not exist in the data. Now, with those important technical caveats out of the way, let's have some fun. We've pasted in our command, and we hit enter. Now we can sit back and watch the learning happen. So you'll see that we've loaded 520 draws from the CSV that was provided in the project. Furthermore, you see that we've included a chance approximation baselines. So in the lottery, it's typical that you would guess one number correctly approximately 14% of the time. You'll see that guessing the bonus number correctly occurs approximately 2.33% of the time. With that said, after we've run with 16 epochs and 4 layers, that our final evaluation of the model actually gets us about 6.6% on the bonus number and 14.24%. But here's what really matters. it got the full set correctly 0% of the time. That's important. And that shows us what true randomness is. Now, for the sake of having some further fun, let's look at what would happen if we up the number of layers to 8. Let's double it. And we're going to up the number of epochs to 32. If you're thinking that this can be run for an extended period of time or actually learn enough to truly guess the next full set of data, it can't. As cool and fun as that would be, it truly can't. And it's because of the reasons explained about the epochs and the layers. It can't create something from the data that doesn't exist. And when randomness occurs, there's no predictive capability in existence. So again, we'll run this updated command and let's see what happens. Is it possible that the training loss drops off? Yes, we would expect it. Is it possible that the main hit rate on the historical data goes up? Yes, we would expect it. Is it possible that the bonus accuracy goes up? Yes, we would expect it. But is it possible for the main hit rate to go up? No. It's not. So you can see the progression for the training loss does decline like we had expected. The final evaluation shows continuous training loss, as we would expect, actually higher than in our first evaluation. The main hit rate does increase to 15.09%, and the bonus accuracy, interestingly enough, actually dropped. So we got to 1.6%. But again, most importantly, and this is the crucial truth behind the model, is that the main exact, it got all of the data correct 0% of the time. And that's with hats off to randomness, my friends. I truly hope you enjoyed this. We're going to work on a couple of more longer form videos in the coming days. I'm glad that you're here. I hope you're learning something. And most of all, I hope you're having fun. Thanks for being here and have a great day. We really appreciate you.